Okay, now we're going to shoot the problem number 11. The previous video shot number 10. In number 10, we had a student moving a box of books down a hall. In this one, we have the same student moving the same set of books up a ramp. So one thing that's not mentioned very clearly in this problem that should be is that the mass of the box is the exact same as the previous problem. So that should just be 35 kilograms on that. You'll also notice the force is exactly the same, the angle is exactly the same compared to the surface, and the mu value is exactly the same in this particular hallway. So, all we've got now is we've got a hill that is 12 degrees. Now, one thing you want to be careful of in these problems is specifically these angles. This says 12 degrees with the horizontal. So if I were to draw a dotted line right here along the horizontal, you can see that this angle right here to the hill is 12 degrees. Then later on in the problem, it says that the force that it's being pulled at, oops, wrong problem here, the force that's pulling it is 25 degrees with respect to the incline. So in other words, if we made a dotted line parallel to the incline, this theta would be 25. So if we wanted to go from the horizontal, yeah, you could just add those up and get 37. But there's probably a reason that it's got those separated. We'll see that here in just a second. So let's get rid of that for right now. All right. So here we go. We've got the we've got the hill here. We've got the hill here. We've got the pull up. I've already done the force diagram for this. Force gravity should go straight down. Force friction should be parallel away from the way it's going. And force normal goes perpendicular. Force tension, you'll see this angle once again is 25 degrees, which is 25 degrees away from the incline like it said in the problem. Similar to the previous problem, the mass is 35 kilograms and the mu value is 0.27. So what we want to think about first in this problem is which direction the object is accelerating. I would say it's probably a fair safe bet to say that it's going to accelerate up this particular incline. Not the direction of this force, but up the incline. So what I want to think about is where my x and y axis starts to begin with. And that would be with the horizontal. So I got to think about how I want to shift this. Well, I want to match the acceleration. Since that's along the incline, I need to move these lines 12 degrees. Not 37, not 25, but 12. So this is going to come up 12, which means this is going to come left 12, down 12, and over 12. Essentially, it's going to go counterclockwise all 12 degrees. So come down to my force diagram to see that. You can see this dotted line actually already nicely along the surface there, which is actually not done very nicely. Right along the surface there already well represents the new x-axis, and my new y-axis should be right down here through force normal. Now that has the added benefit of going through force friction and force normal, but once again, that is not the reason why we do it. And this, as we make a mention of up here, came over 12 degrees. So we need to find acceleration. Similar to the last problem, we imagine the acceleration is along the x-axis to begin with, so we could start there, but we're pretty sure we need to find force friction. So I'm going to start here at force normal. So I'm going to begin summing the forces in the y-axis. Set that equal to mass times acceleration for Newton's second law. Is there any acceleration in the new y-axis? Well, no, that's one of the major reasons we just moved that way, because my new x-axis lines up perfectly with that acceleration, so none of it's in the y. So we cancel that out. Now we sum the forces in the y. Let's start with force normal. It's all positive and entirely in the y. Force tension does in fact have some in the new y, and that's why that angle from incline is actually helpful to leave it there and not to put it at 37, but to leave that guy at 25 degrees. So I'm going to put plus force tension in the y. And then since we shifted the axis here, we can see that this force gravity right over here, let's call this FGY, is in fact along the new y, so I'm going to put negative FGY. And that's equal to 0 because there's no acceleration in the y. Now the purpose of this is to find how much force normal there is. If I had done this a little bit more carefully, I should probably make this force normal a little bit smaller, but it's no big deal for my force diagram. So we isolate force normal by subtracting and adding those two on the other side respectively. So I have minus force tension in the y plus force gravity in the y. Force tension in the y can be seen from this triangle that part of the side is 185, and since it is the opposite of 25 degrees, that is equal to negative 185 newtons sine of 25, plus, we know that this guy is equal to mg. That's the hypotenuse. This side over here, if you look carefully, it's kind of weird to see with my drawing, but that's that 12 degrees I mentioned earlier. So FGY is actually the adjacent part of the new triangle, and thus that needs to be mg cosine of 12 degrees. And you calculate that all out to get force normal. Once you have force normal, you can get force friction simply by taking mu times that number. Don't worry about that right now. And now that we've got force friction, we can sum the forces on the x. So now we sum the forces on the x here, with mass times acceleration on the x. There is acceleration on the x, that's why we did this whole thing. So we just need to sum the forces on the x. I can see that force tension definitely has some on the x, so I put plus force tension in the x. Swinging around here, force normal did not. Force gravity does, and you'll notice that it actually pulls in the negative direction. So I have negative force gravity in the x. Force friction also definitely does. So those are my three. Force tension in the x is going to be a little bit of trig. That's that 25 and is adjacent to that. So that should be 185 cosine of, what is that, 25? Yeah, 25 degrees. Force gravity in the x, I use this triangle once again, and I'll see that my force gravity in the x here is actually opposite of 12. So this should be minus mg sine of 12 degrees. This force friction is what we calculated a second ago, and all we need to do now is simply divide by mass, and there's our acceleration. And that's how you do that. If you need a little bit more instruction on the math, I'd be happy to shoot that in another video.